Okay, guys, welcome. Today we're going to talk about how to use trigonometry to compute the area of shapes. So we're going to start with how to compute the area of a triangle that may not necessarily be a right triangle. We'll talk about how we can then extend that to the idea of finding the area of a parallelogram, and we can talk about how to find angles within there as well. And then we'll talk about how to compute the area of any regular polygon using this idea. And then we'll talk about some approximations that we can do with the trigonometric functions. All right, so the first thing that we're going to start with is that if you have a triangle that may not necessarily be a right triangle, as I draw a right triangle, so let's maybe try and not draw a right triangle, then if you're given two sides that we'll call B and C and the angle between them, then the area of that triangle is 1/2 of B times C times sine of that angle, right? And this is, of course, almost similar to what you think of when you think of the regular formula for the area of a triangle, but in that case, you would need base times height, right? So it's a little bit like that sort of identity there. All right, but let's go ahead and put this in action. We want to find the area of a triangle that has side lengths of 4 and 7 and has a 49-degree angle between them. All right, so by our previous formula, we will find this by doing 1/2 B times C times sine theta. So in this case, we want 1/2 times B, which is 7, times C, which is 4, and then times sine of 49 degrees, right? So these three numbers will combine to give me a, let's see, it looks like a 14, right? So we want to find 14 times the sine of 49 degrees. All right, so if we punch this into a calculator, and again, in this setting, we would want to make sure that we are in degree mode. So we will do 14 times sine of 49 degrees. And again, make sure that you're in degree mode. And you'll find that the area is roughly 10.566 square units, I guess. No units were given here, so we could just say square units. All right, so that would be the approximate area of this triangle here. All right, now, of course, you can manipulate this formula in order to solve for one of the angles, right? You could multiply both sides by 2, divide both sides by B times C, and you would end up with this identity here, which tells you that the sine of the angle should be 2 times the area divided by those two sides. Okay, so let's see an example of that. Now we're being told that the area of the triangle is equal to 6, and it has side lengths of 3 and 8, and we want to find that angle, right? So we know that A is equal to 1/2 B times C times sine theta, and then we just showed a second ago that the sine of theta is equal to 2A over BC. So we could say that the sine of theta is equal to 2 times A, which is 6, over B times C, so 3 times 8. So we get that sine of theta is equal to a 12 over a 24, right? Which of course is sine of theta is equal to 1/2. So now we want to think about what's an angle whose sine is 1/2. Of course, we remember that that comes up in a 30, 60, 90 triangle. So which of these two angles has a sine of 1/2? Well, of course, that's going to be the 30 because its opposite side is 1/2. So in this case, my theta is 30 degrees. Or you could say, if you want in radians, that that's pi over 6. All right, so that's how we can find the angle that would be, and of course that corresponds to this angle. Sorry, not 60, 30. Yeah. Okay, so that's how we can use that same formula to find the angle between those two sides. Okay, now of course we can extend this to a parallelogram, because if you look at any triangle, if you sort of extend the triangle into something like this, by sort of just reflecting that triangle over, what you get is a parallelogram. Right, and adjacent sides B, C, and the angle between them. So of course, it should follow naturally that the area of this would just be B times C times sine theta, because you would double the previous formula, and when you multiply it by 2, it would cancel out with the 1/2. So this is sort of a nice extension from a triangle to a parallelogram. Okay, so now we have that the parallelogram here has area 40, and each of these side lengths are 5 and 10, as we have shown, and we want to find the angle between the lengths of 5 and 10. So we want to find this angle and this angle, right? And of course, they're going to be different. So if I want to find this angle, I need to do A is equal to B times C times the sine of theta, right? Now my area is 40 and my sides are 5 and 10. Right? So 40 over 50, because that's this 5 times 10 that I divide over, is going to give me sine of theta. So now I need to find the inverse sine of 4 over 5, and that will give me my theta, right? So if I find the inverse sine of 4 over 5, I'm going to get that my theta is roughly equal to 53.13 degrees. Now, of course, that's just one of the angles, right? So we get that this is our acute angle, right? So you're going to get one acute and one obtuse angle. How do we get the obtuse angle? Well, we know that these two angles together have to equal 180 degrees, all right? So I have that like theta 1 plus theta 2 has to equal 180 degrees. So then I can get the obtuse angle by doing 53.13 degrees plus theta equals 180 degrees. So the other angle, let me maybe call this theta 1 and theta 2, would be 180 minus 53.13. And if I do that, I'm going to get that theta 2 is roughly equal to 126.87 degrees. All right, so here you're always going to get one acute and one obtuse, or they're both right angles, right? So that'd be the only way that they're both not acute and obtuse. Okay. Now comes the idea of, can we extend this to just any regular old polygon, right? So in this case, in particular, we're dealing with an octagon, all right? And of course, we're going to take here that we have 8 equally spaced points on the unit circle. So here's what I want to do. So let's look at our unit circle. And what we want to do is we want to find the octagon. So that means 8 sides, right? So let's make these the first 4. And then we'll put the other 4 halfway between each of these. So they're all equally spaced. Okay. So now I'm interested in finding the area of this shape that's sort of spanned by these red dots around the unit circle. All right. And what we're going to do is we're going to break this into something we know how to do. Now, if we look at this, we no longer have a right triangle, but that's okay because we've now talked about how to look at one of these things for a non-right triangle. And again, the advantage of using 8 equally spaced points is that if I find this, I need to multiply it by 8 and I'll be in good shape, right? So now comes a matter of, let me sort of do this more to scale. We need to find the area of this thing. All right. Now we could find the area if we had this side, this angle, and this side. Right. But if you look carefully, we can see that each of these B and C's are radii on the unit circle. These are each one. So now it just becomes a matter of, well, how can I get theta? All right. Well, if 8 of these triangles make up an entire circle, then 8 of these angles have to equal 360 degrees. So then I can divide each side by 8, and that gives me that each of these are 45 degrees. Right? So the area of one triangle is A equals 1/2 B times C times sine theta. And in this case, it's 1/2 times 1 times 1, so I'm not going to write them, times sine of 45 degrees. Well, this is 1/2 times square root of 2 over 2. So this is square root of 2 over 4. And that's one triangle. So now to get the entire octagon, so the octagon is 8 triangles. So I need to do 8 times square root of 2 over 4. And once we multiply, we'll get that the area is 2 times square root of 2 square units. All right. So we can break this up into triangles, find the area of one triangle, and then multiply by however many that you need. Okay. So now we can apply this to the pentagon. And we're saying that if we're looking at the pentagon, and we'll assume that it's regular, so it means that all these things are the same, we have that each side is 921 feet. Right, and they're of course all the same. And we want to find the area. All right. All right, so we have something like this. Now, what we can do is a similar situation as before. I can break this up into 5 triangles, find one of the triangles, and then I'll be in good shape. Right? So if we know that this long side is 921 feet, can we find this angle? Well, of course we can, because we know that 5 of these angles is 360 degrees. So if I divide by 5, I'm going to get that 360 divided by 5 is going to give me that each one of these angles is 72 degrees. All right. So what we currently have is that each triangle looks something like this. We have a 72 degrees here. We have this is 921 feet. All right. Now the problem is that we don't know what these sides are. And if we had those sides, then we'd be able to figure out what the area is, right? So what we need to do is we need to be a little bit clever to get that side. So what we're going to do is we're going to drop a perpendicular down here, and we're going to call this part of it 921 divided by 2, because that's half of it. So then that gives me a new triangle that we can talk about, where this is 460.5, and this angle is now 36 degrees, and here we have a right triangle now. So now we can get this length. So if I look at this angle, 460.5 is my opposite and x is my hypotenuse. So we can say that the sine of 36 degrees is equal to opposite 460.5 over my hypotenuse x. And then by rearranging, we could say that x is equal to 460.5 divided by sine of 36 degrees. So we get that x is, so let's see, 460.5 divided by sine of 36. We get that our x is roughly equal to 783 0.45. Of course, this is in feet. Right? So that's what this is, 783.45. Right? But now since all these triangles have the same sort of radius here, we have that this is also 783.45. So now, to get the area of one of these triangles, so area of one triangle, again, using the A is equal to 1/2 B times C times sine theta, we're going to get that the area of one triangle is 1/2 times 783.45 times 783.45 times sine of 72 degrees, our angle. All right, so now we'll let the calculator do this. So we have a 783.45 times 783.45 times sine of 72, and then divide that by 2, and we'll get that the area of one triangle is, let's see, so we get a 291,876.35. So that's the area of one triangle. So the area of the entire pentagon is 5 times this number, because I have 5 of those triangles. So if I multiply that by 5, we get that this is roughly 1,459,381.73 square feet. All right, so that would be roughly the area of the pentagon, at least according to these calculations, right? Okay, so now finally we can talk about some small approximations that we can do with sine and tangent. So if you have that your angle is very small, then the sine of theta is very close to theta, and so is tangent of theta, right? And that's, of course, for very small angles. Now, if your angle is between 0 and pi over 2, we also have this relationship as well, that your sine will be a little bit less than theta, and your tangent will always be a little bit more than theta, right? So that will hold from 0 to pi over 2. All right. Next identity we can come up with is that the sine of theta over theta is always going to be bounded between cosine of theta and 1. This is something that you'll show later on in calculus, right? So you'll talk about a nice, cool way to do that. And then if you have, again, that your theta is very small, you get that sine of theta over theta is approximately equal to 1. And that's also, again, because we said that sine theta is very close to theta, right? So then if you put that idea into here, then you get that's approximately equal to 1. All right. Now, if theta is small, you can say that cosine of theta is roughly equal to 1 minus theta squared over 2. All right, so that's another approximation that we can use. All right, so these are mostly things that you'll look at when you move on and take a calculus course, but these are some approximations that you can do with these trig functions here. All right, so that concludes this video on using trigonometry to compute area. I hope you enjoyed, and I will see you next time.